Welcome back, everyone. Ready for another deep dive. Today, we're going to be talking about something pretty amazing, Californium.
Californium.
Yeah, Californium. You sent over a Wikipedia excerpt about it, and, well, let's just say this human-made element is in a league of its own.
Oh, I completely agree. It's incredible, really, when you think about it. It doesn't exist in nature at all.
Right.
Scientists had to create it from scratch.
So let's take it back, way back to 1950, the Lawrence Berkeley National Laboratory.
Okay.
There was this team of researchers, Stanley Thompson, Kenneth Street Jr., Albert Ghiorso, and the famous Glenn Seaborg.
The legendary team.
They'd already made some groundbreaking discoveries.
Oh, yeah.
But this time, they synthesized californium, the sixth transuranium element ever found.
Quite a feat. And not an easy one by any means.
Definitely not.
They bombarded curium with alpha particles to do it.
Essentially, helium atoms stripped of their electrons,
Yeah.
right?
Exactly. But here's the thing. They only produced a tiny amount of californium-245.
How tiny are we talking?
We're talking 5,000 atoms. You can barely even see that under a microscope.
Wow. And on top of that, this californium-245 was incredibly unstable.
Oh, absolutely. A half-life of just 44 minutes.
It decayed so rapidly, it must have been a race against time for those researchers.
They were working with, they were working with a very short window, that's for sure. But you know what I find really interesting about all this?
What's that?
The name.
Yeah. Instead of following the convention they used for elements 95 to 97, they decided to honor California.
Rather, they discovered it. The Wikipedia excerpt even draws a humorous parallel to the gold rush, saying that reaching californium in the 1950s was as difficult as reaching California a century earlier.
That's a great analogy.
There's a certain pride there, wouldn't you say?
Absolutely. It's like they staked a claim not on land, but on the periodic table, a scientific gold rush of sorts.
Exactly. And it wasn't just a name. This decision really captures the scientific spirit of the time, pushing boundaries, making groundbreaking discoveries.
It took another 4 years before they could actually produce a measurable amount of californium over at the materials testing reactor in Idaho.
It's quite a journey, isn't it? From invisible atoms to something you can actually weigh.
That's incredible. Now, I'm curious, what does californium actually look and feel like?
Well, picture this. A silvery white metal that's surprisingly malleable. If you had enough of it, you could probably cut it with a knife.
Really?
It wouldn't shatter.
It's quite flexible. Californium has a pretty high melting point, too, about 900 degrees Celsius.
Wow, that's hot.
And its estimated boiling point is around 1743 Kelvin.
So it can withstand some serious heat.
Yeah.
But here's where it gets even more interesting. Californium exists in two different forms, alpha and beta.
Mm-hmm.
And these forms change depending on the temperature. If you apply enough pressure to the beta form, it even transforms into a distant structure.
That's right, the orthorhombic structure.
The Wikipedia article mentions something called 5F electron delocalization, which sounds pretty complicated. Can you break that down for us? Think of it this way. You've got these tiny electrons whizzing around inside the californium atom.
Okay.
And there's this specific area called the 5F orbital, where some of those electrons like to hang out. Now, when you squeeze californium under pressure, it's like squeezing those electrons together.
I see.
They start bumping into each other more, and they become less confined to their individual atoms. It's like they spread out.
So it changes how the atoms connect.
Exactly. This delocalization of electrons actually changes the entire structure of the californium crystal. It's like rearranging building blocks to make a more compact and stable structure.
So under pressure, californium adapts by rearranging its internal structure.
That's fascinating. And speaking of structure, the excerpt mentions that californium has a relatively low bulk modulus compared to other metals.
Right.
What does that mean, practically speaking?
Bulk modulus is basically a measure of how resistant something is to being compressed. Think of it like a squishy stress ball versus a solid steel block.
Californium, even though it's a metal, is closer to that squishy ball in terms of compressibility. It's not as rigid as, say, iron or aluminum.
So we've got this element that's human-made, incredibly rare, can change its structure under pressure, and is surprisingly squishy. Now let's dive into the chemical side of things. The Wikipedia article says that californium has multiple oxidation states.
Yeah, +2, +3, and +4.
What does that mean for its reactivity?
Well, that's where californium's personality really comes out. Those different oxidation states mean it can interact with other elements in a variety of ways.
How so?
For example, in its +4 state, it's a really strong oxidizer, meaning it loves to grab electrons from other substances.
Okay.
But in its +2 state, it becomes a reducer. donating electrons instead.
So it can be both a giver and a taker?
Precisely. It's almost like it has a dual personality in the world of chemistry.
That's fascinating. And the excerpt also mentions that it reacts with various elements like hydrogen and nitrogen. It even tarnishes in the air, especially when there's moisture present. It sounds like a pretty lively element.
It certainly is. Its behavior in solutions is interesting, too. Californium is only soluble in water when it's in its +3 state.
What happens then?
Well, it forms what we call Californium cations. These cations can then bond with other ions to form various compounds,
Like what?
like chlorides, nitrates, perchlorates, and sulfates. Those are all soluble.
Wow, that's a lot of chemistry.
But there's one more thing about californium that's quite unique. It shows covalent properties.
Covalent.
Yeah, like sharing electrons. It's unusual for heavy actinides. It's like finding a penguin in the desert. It really challenges what we know about these elements.
So, to recap, it's incredibly rare, changes under pressure, has this dual personality when it comes to reactions, and breaks the rules of bonding. That's a lot to take in. But there's another layer to this story.
Isotopes.
Right, isotopes. What role do they play in all of this?
Think of isotopes like different versions of californium, each with its own weight class, you could say.
Okay.
Each isotope has a different number of neutrons in its nucleus. That affects how stable it is, how radioactive it is.
So it's like a family of californium atoms, each with its own quirks. The Wikipedia excerpt highlights the most stable ones, Californium-251 with a half-life of 898 years.
That's a long time.
Californium-249, 351 years. And then there's Californium-250, just over 13 years. Those are some pretty impressive lifespans for radioactive elements.
Absolutely. They're the well-behaved siblings, you could say.
And then there's the wild child.
Exactly. Californium-252, intense radioactivity, relatively short half-life, just 2.645 years. But what makes it so fascinating is how many neutrons it emits.
I remember reading about that.
It's a lot, like 2.3 million neutrons per second, and that's for just 1 microgram.
That's a tiny neutron factory. It's amazing how something so small can be so powerful. But how do scientists even create these different isotopes?
It's not simple. It's a very controlled process.
The excerpt mentions bombarding other elements with neutrons.
Right.
But it seems pretty complex.
Oh, it definitely is. Take Californium-250, for instance. Scientists bombard berkelium-249 with neutrons in a nuclear reactor.
And what happens?
Well, the berkelium captures a neutron. Then it transforms, and after a series of reactions, it eventually becomes Californium-250, kind of like a chain reaction.
I see. And there's that amazing diagram in the Wikipedia article showing how Californium-253 is made.
Oh, yes.
It starts all the way from uranium-238. It's like a nuclear recipe with all these steps. Neutron captures, beta decays.
Right, and each step is crucial. It's a testament to how much scientists understand about these processes and the level of precision they need.
It's mind-boggling. But all this effort, it leads to some remarkable applications, right?
Oh, absolutely.
The excerpt mentions everything. Nuclear reactors, medical treatments, even prospecting for gold. It seems like Californium-252, especially, is the star of the show.
It really is versatile. Let's start with its role in nuclear reactors. Remember all those neutrons it releases?
Billions of them.
Well, they're incredibly valuable for jump-starting the nuclear chain reaction in a reactor.
So it's like a spark plug for a nuclear engine.
Exactly. A very important role. But its applications go far beyond that. Have you heard of neutron activation analysis?
Sounds familiar.
It's a technique where you bombard a sample with neutrons from Californium-252.
Okay.
And by analyzing the radiation that comes out, you can figure out what the sample is made of. You can even detect tiny amounts of specific elements.
So it's like a fingerprint for materials.
Precisely. And it's used in a lot of different fields. Environmental monitoring, even authenticating artwork.
That's amazing. And then there's the medical field. Californium-252 is used to treat cancer.
Yes, in a procedure called brachytherapy.
How does that work?
They implant these tiny capsules of Californium-252 near tumors.
Wow.
The neutrons it emits, they have a lot of energy but a short range. So they deliver a very targeted dose of radiation to kill the cancer cells while minimizing the damage to surrounding healthy tissue.
It's incredible how something created in a lab can be used to fight cancer. And the applications just keep going. Fuel rod scanners, aircraft inspection, even metal detectors. It's a Swiss Army knife of an isotope.
It really is. The way it emits neutrons makes it perfect for what we call non-destructive testing.
What's that?
It's basically a way to see inside objects without having to cut them open. Like with those fuel rod scanners, Californium-252 is used to check for any cracks or problems in nuclear fuel rods.
That's so important for safety.
Absolutely. And for aircraft inspection, it's the same principle. You can use those neutrons to see if there are any hidden cracks in the wings of a plane, for example.
That's amazing, like giving an airplane a superpowered checkup.
Exactly. And then there are the more everyday applications.
Like metal detectors.
Yes. Californium-252 can be used to make these portable detectors that are really sensitive. They can be used for security or even to find buried treasure.
That's awesome.
And in prospecting, Californium's neutrons can help you find valuable minerals, like gold or silver.
It really is an incredible isotope, so many different uses. It really shows how creative and resourceful scientists and engineers can be.
It does. But, it's important to remember that Californium, while it has all this amazing potential, it's also a radioactive element.
That's a good point. We've talked about all the good stuff, but it's important to be aware of the risks, too.
Exactly. The Wikipedia article mentions that Californium can accumulate in our bodies.
In our bones, right.
Yes. Its chemical behavior is similar to calcium, which is a key component of bone.
And that's a problem because...
Well, because Californium is radioactive. And if it builds up in our bones, that radiation can be harmful. It can disrupt the production of red blood cells.
So it's not just about the immediate effects of radiation, there are long-term consequences, too.
That's right. And although we don't encounter Californium naturally, there are certain jobs where exposure is a real concern.
Like people who work in nuclear facilities.
Exactly. Researchers, anyone handling Californium in a lab, even some medical professionals who use Californium for cancer treatments. They all need to take precautions.
That makes sense. It's like handling any powerful tool. You need to know what you're doing.
Precisely. And it's not just about protecting ourselves. It's about protecting the environment, too. We need to make sure Californium is handled and disposed of properly so it doesn't contaminate our water or food.
It's a good reminder that scientific advancements come with responsibilities. But speaking of potential risks, the excerpt mentioned Californium-251 and its incredibly low critical mass. That sounds a bit unnerving.
It's definitely something to be aware of. A critical mass is the amount of material needed to sustain a nuclear chain reaction.
And for Californium-251?
It's only around 5 kilograms, so a relatively small amount could, theoretically, cause a lot of problems.
It's a bit scary, honestly.
It's a reminder that Californium, with all its benefits, can also be dangerous. That's why there are strict regulations around it.
So even though Californium-251 might not be as widely used as Californium-252, its properties still make it a subject of a lot of interest, both scientifically and for security reasons.
Absolutely. It's a delicate balance, isn't it? Harnessing its potential, but doing so safely. But before we wrap things up with Californium, there's one last aspect we need to explore. Its role in creating other elements, like oganesson.
That's right. It's amazing to think that an element that didn't exist naturally is now being used to create other elements that are even further down on the periodic table. It's like a scientific chain reaction of discoveries.
It really is remarkable. It shows how interconnected scientific knowledge can be. Studying one element can unlock the secrets of others. Californium's a perfect example. It was key to creating oganesson.
Oganesson. Element 118, way down there on the periodic table. The excerpt says they created it by smashing calcium-48 ions into Californium-249.
Right. They used a special particle accelerator to do it.
That sounds pretty intense.
It is. The collisions were so powerful that they actually fused the nuclei of the two elements together. And that's how they got oganesson.
A brand new element, just like that.
Well, not just like that. It's an incredibly complex process. A lot of precision and a deep, deep understanding of nuclear physics involved. But what's even more fascinating is that oganesson is a noble gas.
Like helium or neon.
Exactly.
Yeah.
But with a much heavier nucleus. It really pushes the boundaries of what we know about the periodic table and how elements behave. And to think all of this was possible because of Californium, an element that was synthesized in a lab.
It's a real testament to how one scientific breakthrough can pave the way for another. But as we wrap up our deep dive into Californium, we should probably touch on the precautions again.
Good point. We've covered a lot.
We've talked about its history, its properties, all the amazing things it can do, and of course how it's used to create other elements. But we can't forget about its radioactive nature.
Right. That's a crucial part of the story.
The Wikipedia excerpt mentions that Californium-249 and Californium-251 are considered radiotoxins. Why is that? What makes them so toxic?
Well, radiotoxins are substances that are not only radioactive, but also have a chemical toxicity. They can damage biological systems.
Okay.
Californium-249 and Neg-251, they act a lot like calcium, which, as we discussed, means they tend to build up in our bones. And that's where the problem lies.
Because the radiation emitted can cause harm.
Exactly. It can disrupt the formation of red blood
And
cells,
leading to...
anemia, other health complications.
Hmm.
It's not just about immediate radiation exposure. It's about the long-term effects of californium accumulating in the body.
So even though Californium isn't something we find naturally, there are still situations where people need to be extremely careful.
Oh, absolutely. Anyone working in nuclear facilities, researchers in labs, even some medical professionals who use californium for treatments, they all need to take precautions.
What kind of precautions are we talking about?
Well, first and foremost, protective gear. Gloves, respirators, special clothing. It's crucial to prevent skin contact and inhalation. And the environment where they're working needs to be carefully controlled.
To prevent contamination.
Exactly. Specialized ventilation systems, specific procedures for handling californium, and of course, regular monitoring to check for any radiation exposure. It's all about safety.
It sounds like handling Californium requires a lot of knowledge, caution, and respect.
It does. It's a powerful tool, and with that power comes responsibility. We have to be mindful of both its potential and its risks.
Well said. So Californium. It's a fascinating element with a captivating story. Born from human ingenuity, it holds the potential to shape our future in remarkable ways. But as we've learned, we need to approach it with both enthusiasm and caution.
I agree. It's a powerful reminder that scientific progress isn't always a straight path. There are always new challenges, new discoveries to be made. Who knows what the future holds for californium?
Maybe it'll help solve some of our biggest problems, like global energy or finding cures for diseases. Or maybe it'll unlock even more secrets about the universe. Whatever happens, it's sure to be an exciting journey. We encourage you to keep exploring. There's still so much to learn about this incredible element, and until next time, stay curious.